right. Oh yeah, if you can't see, I'm wearing my Binary Ninja t-shirt that Jordan gave me at Recon, which is pretty cool. So, okay, yeah, so I also saw Leon on the stream. So Leon, quite a while ago now, like I think in like April or something, did a blog on this Donex ransomware, or Donex, sorry. I think it's Donex. And this has a crypto flaw in it, so I thought it could be fun to look at. I also wanted to mess around with the new version of Sidekick. So as some of you may have noticed, I haven't streamed in quite a long time, since like June-ish. The reason for that was just because I was doing a whole bunch of conference travel during the summer, and then I was trying to get this Binary Ninja edition of the course done. So that was kind of the main reasons for that. But during that time, the new version of Sidekick came out, which has like a really cool feature set that I wanted to take a look at. So I thought we could mess around with this ransomware sample and check out some of those new features. Does that sound good? Oh yeah, I should probably link the new course too, actually. So let me put that in chat in case anybody's curious. Needs to get less Chrome windows. Yeah, so if any of you want to check out the course, there's a direct link there. One other weird thing that happened when I put up the commercial, so like the video that is on that webpage, this thing, I put that on YouTube, and then a few folks mentioned that they weren't able to get to that training subdomain. And when I looked into it further, I guess one of the US ISPs were blocking the training website. So I do know that can happen sometimes when there's like malware related content on a website and then they get blacklisted. But if any of you can't access the website, that's why, is your ISP might be blocking it. So maybe try on your mobile internet or something like that, which isn't great if you're trying to like watch videos and stuff. But I'm trying to get it removed. It might have already been removed from that particular ISP, but I just wanted to mention that. Not great when you're trying to put out content and then folks are blocking it. So, okay. So yeah, let's take a look at this. Yeah, binary.ninja, we are gonna take a look at Sidekick. So the new stuff. So I know there's like this new workflow here. So I know there's this new investigations pane that I haven't really looked at. There is this assistant. So for those of you who are not familiar with Sidekick, basically it's like a large language model integration into the Binary Ninja database. And then you can query a whole bunch of large language model APIs in order to interact with the database itself. In order to extract and interpolate information from the database itself. So it's pretty cool. I have a YouTube video on Binary Ninja Sidekick 1.0 on the YouTube channel. I can link that too. Should be pretty fast to get to. If you want to check out the first video that I put out on this, it kind of goes over these different panes. But now I know there's this new one in the bottom right here called Analysis Workbench. So let's take a look at this stuff. And basically you have these scripts that were generated by the large language model that can be used to extract information from the database. So if I just do edit script, then this is that too tiny for you guys? So there's this concept with Sidekick as well called, I'm going to probably butcher a lot of these explanations because I haven't used the indexes a ton, but you can basically perform automation tasks and then classify certain functions based on the automation within a given index. So that's why it says like with open index, the binary view is effectively the binary view is effectively the interface into the open binary within Binary Ninja. So it's using, with an index that is called classify calls, it is essentially mapping out the calls here, I believe. is all this is doing. So if I hit run, hopefully this just worked. Running. Okay. Did it do anything? What would be my indexes? Oh, cool. Yeah. Okay. So, okay. So now that we ran that kind of index classifier, here, I'll get rid of this Python console. So now that we ran this like index classifier, I believe, okay, yeah. So with the index that we created here, classify calls, then it added a category, and the category name is probably the function name or something. Is equal to the, okay, yeah, the category is, oh, right, okay. So what's cool about this is it's classified every type of call here to one of these categories. So network IO, for example, is classified using these WA startup and WNet open enum. And then we have like WNet open enum again, open enum resource, add connection. Those are also network IO. Memory management, obviously we have like all these memset calls and stuff. We have built-in memcopy calls that are classified as the same security strings. So if you were wanting to, I guess, look for vulnerabilities and stuff in this binary, these classifications would probably be very useful, like memory management and string handling. Also interesting for malware research, but cool. So let's try. Okay, so the other thing that I wanted to try out is for enumeration. So I know it can like sub out to looks good. Okay, I was sold just by the theme option Binja, the clean look, and multi-window features. Yeah, I do also like the multi-window features a lot, and the sync. Like this kind of stuff is from or I think they probably got inspiration from Ghidra, but I like the side-by-side views as well. And then you can do like multi side-by-side views. Anyways, before I get distracted by chat, if we go back here, I can write a new indexer here. So I can be like, find all cryptography related calls. And then Sidekick is going to use the large language models to do that. Crypto detector. Okay, yeah, so this is what's cool in the new version. I don't know if I have the large language model operators set up correctly. I'll try to get it set up, but let's see if this works. Yeah, the crazy thing about this is it will like sub out to a large language model operator, and then it'll try and classify code using the large language model, and then integrate that back into this indexer script. So hopefully this works out of the box. I didn't have time to prep all this before stream, so we're kind of going at the seat of our pants here. I know it looks like it's really slow. Maybe not that slow. I know that this would probably be a lot faster if I had local language models. So how this stuff works, I don't really want to mess around with it while Sidekick is running. But it will essentially take all the parts of the code within the database, I believe, within the pseudo-C format, and then query the large language model remotely with all that code. I don't believe in the same LLM context, but it'll then try and classify it based on this like LLM operator string. So this is obviously running very slowly. So maybe we can try reversing this while that's running. Maybe I should have done something more basic. Let's see execution details. Hey, D Pirate Roberts, how's it going? Oh, thanks for pinning that, Bill Friends, by the way. Okay, so what are we reversing? We're reversing this ransomware variant called Donex. I believe that's what it's called. Yeah, Donex. Okay, so while that classifier is running, It's only at like 10%. So we can start looking at this manually without the magic of automation. So in Binary Ninja, you'll get put into the start function. And in this instance, this is like standard MSVC stuff, I believe. So if I go to if I hit Command P on Mac, I can go to the triage view. And this will basically give you like a general overview of this binary. And we can see here on the right hand side that the compilers used that were identified were Visual Studio 2017. I don't know if that's the version of Visual Studio that the malware author actually used, but still pretty useful. Yeah, Albie, how's it going? We're making automation for analyzing malware using large language models, hopefully. Virus. We're analyzing viruses, we're not making them, but okay, so what's your view on AI affecting malware analysis? Hold on, I'm gonna answer your question in 2 seconds. I'm just gonna finish this thought. So we have this imports pane here that basically goes over all the imports that are within the import section of the portable executable, and then these are mapped to a virtual address like as they would be mapped in memory within the import address table. But this just links to the section that contains the import information in the PE. So if I click on this, it automatically goes in our disassembly view here, it goes to the address of that particular import. And then you can see the cross references in the bottom left here. It's hard for me to see because my camera's in the way, and yeah, so you can look at the imports this way in the triage view, and then you can look at the section permissions and stuff like that. And then the strings as well. So pretty useful for when you're looking at the triage information. Anyways, the whole point being is that because it's using Microsoft Visual Studio for compiling this, then we're gonna have a bunch of stuff before the actual main of the malware. So sorry, I'm just gonna open up, go to start again. So there's like the security initialization cookie stuff that was identified. And then this is all like MSVC boilerplate stuff. But if I go to the sub 403 5C0 function, then we can see that there's this show window call. This is not a part of like the MSVC boilerplate. So in IDA, I think the win main function, which is effectively what this is, would be identified automatically. So maybe that's something that they can add in the future. But if I go to this first function call here, we can see that there's a call to create mutex. So this is all very common functionality in malware to determine that only a single instance of the malware is running. So in this instance, they're just creating the mutex, check mutex. So if you were like an antivirus vendor, you could look for, you could hook the call to create mutex and then see if the mutex being created is check mutex. And if it is, then you could just terminate this process because you know it'd be this type of ransomware. And then that's the first thing it does, or like an EDR or something like that. So pretty useful. Then there's this move to this XMM register, and then there's these XORs. So that's pretty interesting. And it's all these A9s. So I don't know why that might be the case, but it might be interesting to look at. And then that's XORed again here. So that might be something interesting to look at. And then we have another call here to this function, which calls a bunch of other functions. Looks like based on the strings, it might be related to UTF parsing, UTF-8 parsing. Interesting. Let's see what else we have here. We have iswow64 process being called. So it's probably looking for the CPU architecture. Get process is being passed to this result. So it's essentially resolving iswow64 process and then calling that with the current process handle. And then, oh, it's just using this for the FS direction stuff. Okay, so here's some crypto calls. So here's probably the meat and potatoes of this ransomware. So we have a few things here. We have cryptgen random. So that's probably generating some sort of key, heap allocation, and then a whole bunch of XMEM registered stuff. Okay, so these are 32-bit XMEM registers, but this is probably related to the crypto operations, and then a modulus operation here. So this is probably encrypting stuff. Okay, cool. And then they empty the recycling bin, which is also very common for ransomware to do. So yeah, this call analysis, take it all. Okay, so yeah, Whitting Sun, it's Donex Ransomware. So Reroot said, what's your view on AI affecting malware analysis? Will this just act like an assistant, or could it even damage the job side? Right now, I'm not quite sure, to be honest. I think there's quite like the space is moving so rapidly that it's hard for me to predict where things are going. But my general opinion is that, like, if these tools are going to be taking over certain functions, you should probably learn how to use them. But don't replace the kind of core underlying understanding of how these things work, because who knows, like, they might always not be great and be really good at misclassifying things, and that's not what you want when you're performing malware analysis. D Pirate Robert said, I think AI will take care of the general repeated stuff, and we would ultimately need a human to connect everything together and look over complex decompiled code. Yeah, exactly. So expected string or bytes like object. Hopefully that didn't just die after all those queries. Oh, that's cool. For your work degree, did you get a degree in cybersecurity or something? But yeah, I pretty much agree with what D Pirate Robert said. I think it's probably going to be ever important for doing monotonous, like, low-hanging fruit basic tasks, but I think for more complex general analysis it'll be harder. There was actually a Google blog on this. Let's see if I can remember. It was like Gemini LM malware analysis. Yeah, this thing. So basically they like decompiled the entire code using this might be the first one. There's two of these. Yeah. Okay, yeah. So what they did was to test out Gemini, which has like a really large context window, so you can have like a whole lot of tokens that that it can analyze. They decompiled a whole bunch of different malware samples using IDAPRO Hexrays, like the Hexrays plugin. And then they dumped all those tokens into Gemini, and then they asked it to basically analyze the full piece of malware. And I think that they got some pretty cool results. Like it was high level insights, but it did a good job, and it like extracted IOCs and stuff, which is like pretty interesting. Hey, Robert Yates, how's it going? What if Gemini was not told that the sample was a malware? Yeah, that's good. That's a good question, actually. I'm assuming their prompt was like, "This is malware." Or wait, understanding legitimate. I think this is what we were just talking about. Even goodware understanding programs functionality can be valuable. The model only receives decompiled code. Okay, it's just saying that it was able to like identify the core functionality of the application. It's still pretty cool though. But yeah, I'd be curious like what prompts they were providing to Gemini before providing the entire decompiled context. But this is like very similar to what we did on like some previous streams with Sidekick. So, okay. Did this finish? Did this do stuff? So the Sidekick coding assistant said, the script iterates over all defined functions in the binary and uses the LLM operator to identify cryptography-related calls. The results are stored in the index cryptography-related calls for easy access. So if we go to the index here and we check out the results of this, oh, this is pretty cool. So result.get cryptography-related calls, add entry, crypto detector. Okay, so must just provide this. This is like a tuple, it's a dictionary for each of these calls. So it says like RSA encrypt. So call to perform RSA encryption. So like, let's look at that address. So again, what happened here was Sidekick sent the decompilation of each of these functions to a external large language model to interpret and then find cryptography related functions. So if we look at this right away, we already see like this call to RSA encrypt may perform. Okay, let's look at this. It says this may perform cryptography operations in its buffers. This looks like the file read functionality. Okay, I should probably start marking these up. So like, I just didn't want to mark up the functions to skew the large language model output for like that call, but w read data maybe. So there's, let's analyze this properly. So we have move file. The new file name is this EDI, or that's the original file name. This is the first argument. Okay, and then if we look at the cross references to this and see where that's coming from, there's a heap allocation. Here, I'm going to mark that up. So heap alloc, the result, if it's not 0, then it returns. And then I'm not sure what this global is, but it returns some global. Okay, let's continue looking at keep doing 2 underscores. So this is called lot for this heap allocation function, so it's good that we marked that up. So I think this might just be a normal copy function. Okay, yeah. So I can, gotta be one of the most patient requiring jobs. Oh, doing malware analysis? Alright, let's see here. Okay, so I think we can probably call this our like main encryption loop, because it's doing find files. It looks like this white folder here is probably a part of some configuration that we can take a look at too. But yeah, I think we should continue looking at, let's call it main enc loop. Let's look at these model responses here. So like, it's identifying like XOR operations and saying they're like crypto related, so I don't know how good that is, but okay. Like if it sees these, then those are definitely cryptography related, so that's good. Checking the config for network shares. I don't see immediately where the, okay, it's just this SBB rule. This function likely performs cryptography related call on the variable var54. So let's look at what var54 does. Oh, is that the other function? This table's kind of hard to read. Okay, yeah, so we can look at var54 here. Okay, that's cool. So, okay, so who can tell me what this expand 16 byte K means if you see that in a piece of malware? Cha-cha, yeah, Zmu, you got it. So, this is performing cha-cha 20 encryption. So let's call this. So this function was also identified by the LLM as potentially performing encryption. So let's call it MW Cha-Cha 20. So for those of you who are not aware, Cha-Cha 20 is a symmetric stream cipher. So it's similar to like RC4 and other crypto-related stream ciphers that it'll basically take a stream of data and encrypt it, unlike block ciphers, which will encrypt it block by block. It'll encrypt it byte by byte. And that's going to be important later because of the crypto flaw in this. Yeah, good indications of Cha-Cha are this expand byte K. And the reason being is that if we just Google this, this is a part of the, so this is just some random Salsa 20 implementation on GitHub, but this is a constant that is used to initialize the Cha-Cha 20 S-box. So if we go to Cha-Cha 20 S-box, or no, sorry, that's a part of the nonce, isn't it? I think it's spelled out here. You get a quick intro what this is. Fix it 42. We're just taking a look at some ransomware and analyzing it using this tool called Binary Ninja. This is my Copilot instance, so I can be like, what is the constant used for? Yeah, it's part of this key setup process. Yeah, so it's part of the initial state of the S-box. But does that mean it's part of the nonce? Okay, so it's part of the key expansion phase. So, yeah, I guess a part of the... Okay, so it's not a part of the nonce. It is a part of the S-box, or like key expansion phase during the initialization. Okay, so let's keep going. Now that we know that's Cha-Cha, we can keep looking at these results from our indexer. And I want to show you one more feature after. So initialize SHA-1 hash. What's up that? So are these constants part of SHA-1? So we can like kind of validate what the large language model results were. Yeah, so like the SHA-1 implementation has that constant, and then the large language model indexer was able to identify that here. So I'm just gonna, so this fill fopen64, so I believe that was either identified by Binary Ninja or that was already in the binary. But this doesn't have symbols, so it might have been identified by the Binja heuristics. Let's see, are these different hashing algorithms? Maybe. Let's look at what these constants are from by Googling them. But these are also SHA-1. Okay, so let's just call the this higher level function. I don't know what. Maybe these are different. Like, see these flags here? These Boolean flags. Let's just call this like MW SHA-1. And what other interesting ones we have here? Applies a combination of XOR and subtraction on integer inputs, which is often used in cryptography. Okay, it's kind of interesting. Potentially process derives a cryptographic key or values from provided parameters. Okay, let's look at this one. What's the description again? 407. Maybe I'll just dump this table. Potentially processor derives cryptographic keys or values from provided input parameters. May execute cryptographic operations such as encryption or hashing. Likely involved in cryptographic output, potentially handling cryptographic computations. Okay. Why? This does like, these are a bunch of modulus and like adds and stuff. The high level ILS, like the Mulu DPD, that's kind of weird, but oh no, those are multiplications, I believe. Not modulus, sorry. And then adds. So yeah, this definitely looks like cryptography related. Let's see where this is called. Okay, this might be RSA related. Okay, so this is probably the global encrypted key. Look at these cross references again. Man, not good, can't replace it. I'll fix that for next stream. Okay, it's writing this encrypted 16-byte value to a file. So this is probably part of the file footer. I haven't analyzed this ransomware before, by the way. This is all just like guesswork, but this is probably the encrypted, and then, but it's setting the file pointer at the beginning. So I don't know if that's right. I'll be more responsive in chat, I promise. So this new tool, what OSs does it work on? Free version or open source, paid? Yeah, reroute. Answer all the questions. Thanks, reroute. So let's keep looking at those indexes. And we can mess around with some other stuff. Yeah, crypt acquire context. It found acquires that handle cryptographic service provider. Crypt gen random. So yeah, like all the stuff we just identified manually before, so that's cool. This is probably used for key stuff. And this looks like a structure that the function pointer is being assigned into. So let's take a look at the others. XOR operation. So a ton of XOR operations in this. So yeah, again, this looks like cryptography related. Not like super helpful when it's just like this does XOR, but provides no other indications. SHA-256 constants, that's really cool. I like the fonts and colors. I was fighting with streaming immunity debugger on a buffer overflow learning room yesterday, where I had no control over the tiny font. Oh yeah, Windows 7. Did you get the buffer overflow to work? I remember using immunity debugger. Oh cool. Okay, so that SHA-1 function that I looked at earlier. This is also SHA-1 related. Like what I thought these, I didn't know what these booleans were for, these other calls, that was SHA-256. So it's no longer just SHA-1, we just renamed it to SHA-hash. So I wonder what these mem copies are. Oh, it's just these constants. So it's probably another crypto related stuff. Yeah, okay, SHA-256. Alright, and then, okay, so it's used in a couple places, in a bunch of places rather. Okay, I'll just move through the rest of these and then we can just kind of move through this properly rather than trying to use these LLM outputs. XOR, subtraction, board operation commonly used in large integer arithmetic. That's kind of cool. Oh, cool. Thanks, Hacking Carrots. Yeah, looking forward to seeing your progress in the course. I was talking about it earlier, but it'll be in the stream recording. Right rotations. So yeah, it's just kind of a lot of these are looking at security cookie. That's funny. I guess that's also cryptography related, but not really relevant to the malware stuff. I'm gonna write one more indexer while we're analyzing this, unless there's some other interesting indexes. Okay, yeah, so this is kind of what I was talking about earlier. So those operators that this LLM operator down here was essentially calling out to the Sidekick API. But say I had Meta's Llama, like this is an Intel Mac, so I can't run large language models on it because it uses non-NVIDIA GPUs. So I don't even know if I can run large language models on these video cards. But say I have like an M2 Mac, and say I was running it on there, then I could use these models locally for this LLM operator to call out to. So that's really cool. But basically this was just using the Sidekick API to identify all those crypto related functions, but still pretty cool. Yeah, Hacking Carrots. There's not really any prerequisites. Typically I suggest having a little bit of programming experience and Microsoft Windows knowledge. Being able to like write command line commands, and then yeah, having a little bit of programming experience, knowing how like network connections work and stuff like that, but nothing too intense. Fix it 42. I did a Win10 one using x64 debug the other day. So much nicer. I felt transported back in time. No, I'll hop back into it. Might finish it upstream too hard trying to just read stuff and trying to get people to see. Yeah, I find trying to learn new concepts on stream can be difficult, but it's cool that you were doing that. Yeah, Hacking Carrots, if you have any other questions, let me know. Or anybody for that matter. Okay, let's keep looking at those indexes. Yeah, maybe I'll probably do a Sidekick 2.0 video, so I can probably figure that out later. There we go. So you open the malware program in this tool, and it gives you tips in the cell contents box. Yeah, this is kind of like advanced stuff. This is a plugin that you can use separately with Binary Ninja called Sidekick, and then it'll interact with like large language models that Vector35, the company that created this program, has set up in order to interpret the disassembled and decompiled code. I believe it primarily uses the decompilation on the right hand side here. And then these indexes were basically like the results of this program it ran that was basically asking questions to the large language model about the program. Hopefully that makes sense. Yeah. Okay, let's keep going. How much ASM is 2H then? ASM? Yeah. Assembly can be hard. Initialize SHA-1 hash. Okay, we already found that one. RSA encrypt. Okay, so we already found that one. Encrypt acquire context. Encrypt gen random. Okay, so these are those operations that I identified earlier. That might be PRNG related actually. Okay, I think that's a key, yeah. Yeah, it's 32 bytes. So this 16 byte value, if it's a 96 byte nonce, it's too long for that, etc. So this might not be a key, but we'll see. Okay, and then this is creating some icon, looks like. Get environment variable, common get env. Gets a value of the current environment from the current environment. Yeah, it's just getting an environment variable. And then WB, so is that the environment variable? So this is creating a bat script. And then executing it. So we'll figure out exactly what it's doing later, but exec. Any tips for ways to get started with analyzing binaries like malware? I've worked in IT since '96 and programmed long before that. Yeah, like there's a ton of free resources online. We put out a lot of free resources like these streams. We also have a malware analysis course that I was talking about earlier. Not to just be too pitchy all the time, but I'll send this over to. But yeah, these are like the courses that we do in addition to like all this free stuff. And either of those are a really good place to get started for analyzing binaries like malware. But yeah, you can find a ton of really good resources online. There's like if you join our Discord, I'll plug our Discord too. The course isn't free, but you can like check out some of the modules for free. But if you join our Discord, oh wait, it's not, this is the channel link. Sorry, there's the invite link for Discord. But yeah, I pinned like a whole bunch of free reverse engineering resources in our Discord. So rather than me just trying to like rattle them off the top of my head right now, that's a really good place to check those out. Okay, so back to the malware. Okay, so kill keep. So okay, I really want to figure out this config stuff. Yeah, no problem. Because as you can see, like there's this references to kill keep, and then there's a bunch of references to this function that's getting these config params throughout the ransomware, it looks like. So let's figure out where this config is and then decrypt it, because it's probably encrypted. I think that's a good next step here. So yeah, the large language model indexes were pretty cool. I think we can probably find some more interesting use cases. Oh yeah, there's one I was gonna run. So it could be like, find all the malware related operations. Or wait, I can do... Oh no, I have to go back. Oh, script title, find... Find all malware related operations. So again, this is generating that script for us. Functions. Yeah, let's do functions instead. Instead of so is this function related to malware activities? Yes or no? Let's try that. Again, this is going to take a while because it's going to be hitting the API a whole bunch, but we can analyze the body ourselves in the meantime. I don't know if me renaming functions to MW underscore will affect the results, but okay, so we can look at the code from the start function, but I'll also look in like, sorry, Whitting Sun. Is that better? Or well, the song just ended, so it's not gonna be a good example. Okay, so let's keep going. Oh yeah, I was gonna Google this and see if it's related. Meta CPAN. Well, I think CPAN is related to Perl, so I think that's not what we want. I'm pretty sure it's OpenSSL related. So they probably statically linked some OpenSSL code in here. Let's go back. Yeah, see like all of these cryptographic constants are in here. Object identifier database. What was that? Source code. There's source graph. Can I use this for free or do I have to pay for it now? Book a demo. I guess they don't let people use it anymore. That's good, we can just keep going statically. Grep.app, yeah, that's what I was thinking of. Thanks, old friends. Harmony OS. Dolphin EMU. It's all this OID.c. But what is that from? Object identifier database? Part of embed TLS. Okay, so they're probably using embed TLS for this. Is a C library that implements cryptographic primitives. Okay. So I'm just gonna take some notes, which I probably should have been doing from the beginning, but so uses embed TLS. Okay, so if we go back here, so these are, so I don't really want to reverse the embed TLS code. So I'm probably not going to mark up this stuff from these strings that I saw earlier. But if we go back to our start function here, or not start, but the kind of main handler function, this one, then we have these XOR operations, and then couldn't really see this, probably could have seen it if I kept looking in these sections, but there's this large encrypted blob, right? So this is probably the configuration. So if we look at the cross references to this encrypted blob, then we can see that this is being passed, or this is being XOR'd with these XMEM registers for 21C0 bytes. And then it's adding 64 bytes on each iteration, and then it's doing an XOR with hex 40 or 64 bytes on each respective address right here. And as you can see, it's doing that amount of iterations, and it's adding I to each of those iterations. So it's going to be the next 64-byte block relative to the beginning of each of these blocks that's decrypting using those XMMs. So what we can do next is establish what's being XOR'd here, and it's these 9s, right? So I think these are probably compiler optimizations, and this is simply copying, it's assigning these bytes to our XMMs here. So this is just doing an XOR operation of 64 bytes on each iteration of this for loop. So if I get those bytes, so this block here, let's see if I can pull up the Python console. So I'm just going to hide our LLM assistant here. And then I'm just going to use bv.get bytes, same use to IDA, bv.read, and then this address. And then we're going to get the size here of 21C0. I don't know why these are different, but we'll see. What was wrong with that? I put an extra X for some reason. Okay. And then I'm going to assign this into a buffer here, or well, a Python object. Okay, so we've assigned that to this buffer. And then I'm just going to straight up XOR it with 09 byte by byte, but rather than doing this like crazy 64 byte block variant that they have here. I think this is probably just like a compiler optimization. So let's see, I'll do A for B in A. So for each byte in our A buffer here, I'm just going to XOR it with hex 9. So let's make this, so we'll do result is equal to bytes. So an empty byte array, or bytes object, and then B XOR hex A9 plus equals, or not bytes, result plus equals that. And then you just have to do this like stupid, we're gonna have to cast it, I believe, because it's two integers being XORed together. So then I think it's, if I recall, it's like 2 byte, byte order, little, 2 bytes, and then the length is 1, and then result. So yeah, I thought at first it was a multi-byte XOR, but maybe that's going to be something related later on. But if we look at what I just decrypted here with that single byte XOR using the Binary Ninja Python console, we can see this is like an XML file, and then this has a bunch of XML entries. So those config calls that I was looking at earlier were most likely just accessing these XML nodes within this XML config file. And then they were used throughout the... Okay, so now that we have the decrypted config, I'm going to add that to our... I'm going to print that. And then we're just going to decode it as ASCII. And this icon, maybe, is this truncated? Did I not decrypt the entire config? Maybe this is the full size. Let's try it again. It's definitely truncated. And by that I just mean, it's not the full size. 21E7. Anyways, now we can rename this to config. And then this is going to be probably XML related stuff, yeah. I'm just going to name these like parse XML. And then I think I have to make this like an array. So if I make this an array of, what was that size? So char, I thought that would let me rename this as a variable. Oh, here, I just have to, I have like a separate machine that I'm monitoring here, and I just have to plug it in. 2 seconds. So let's take a look at this config. So it's no longer truncated, which is good. So let's print it to get rid of the \ns. Oh wait, no, we want to decode it as ASCII and then print it. There we go. So because it was a byte array, I did decode it as ASCII. See, now we get all these nice little new lines. And then I'm going to put this in our notes. It's decrypted using a single byte XOR loop with 0x89, and results in the configuration. So if we look at this config, we can see a few things. So white extensions probably means that it's whitelisting these, or like blocklisting these. Yeah, so it doesn't want to decrypt these file extensions, right? So like .dll driver exe, like this would mess up the operating system. And then white underscore files, it's gonna be the same thing, but just file names that it doesn't want to encrypt. So like boot manager, autorun.inf, whatever. So those are just file names that it doesn't want to encrypt during the encryption operations, because it'll make the system unstable. And then these look like folders. Yeah. So any of these folders, white folders. So the recycling bin, config, MSI, I don't know why that's in there. I think these are all like alias Windows stuff, Windows boot program files. Like this could mess up the operating system. And then kill keep, this is probably, I don't know what that keep would mean. Maybe those are the processes that it's killing, I assume. Is it in the whitelist folder? Oh yeah, you're right. Nice. That's funny. Yeah, the last bytes do not fit. Oh yeah, DMOC. Okay. Yeah. Okay, I see what you and Ilfrans were saying now. So that makes sense. So I'm just gonna call this malware main. And then let's go back here. So kill. Okay, so then there's a bunch of booleans. So like black DB. I'm not sure what those are. These are services that it's going to terminate, I assume. And then so it has network share encryption, most likely, kill processes, kill services, shutdown, delete event logs, WMIC shadow copy, VSS admin. Okay, so these are commands that it's going to execute to delete shadow copies. And then this is the ransom note content that they write to each system, and they have some like other information, and then they have this icon that we were kind of seeing earlier. that they most likely replace with the ransomware extension or something. Like files encrypted by the ransomware, they're probably setting the icon to that. So yeah, so always good to get a look at the config so you can get an idea of what functionality is probably going to happen when this thing runs, and what's like customizable in the ransomware. So now what's cool about having the decrypted config XML node names is that we can look for these in the binary, right? So like white extends, if I copy this string, and then this is just assuming they're not encrypted, but we have the string here, and we can look at the cross references for that global, and then we can rename this to white extends conf, for example. And if I go to that, then we can see this is where the whitelist extensions are accessed, right? And then it's doing a string and string. So this is doing a whitelisted, or let's just call it block listed extension comparison. So if it does a string and string and it sees that it is indeed a block listed extension, then it goes to this label. So assuming it doesn't encrypt that file. So maybe don't. And then otherwise, it copies the file name into, it does these copy operations. And this is probably used later on. And then, okay, so we have the like whitelisted file stuff too. Okay, so the ransom note is readme, or ransom note name. This is just calling vsprintf, or vswprintf rather, if I can type. And then let's see what else. Probably make more real estate room here since we're not using the strings that much. Okay, so this is the ransom note name. It's converting to a multi-byte wide string, and then let's see. It's just going to be writing the the content. So if we look at our config, then the content is going to be the ransom note content, right? So this is going to be the get XML config node. Or yeah, let's call it config node. I didn't mean to put that equals there. Okay. So we can call this write ransom note. And if we go back here, oh, thanks, thanks, ill friends. I don't even know what that said, but appreciate whatever you did. Hey, Andrew, how's it going? Thanks for the congrats. Yeah, what time is it in Australia? The morning? Yeah, so it's definitely the key. 6. You didn't have to, I hope you didn't wake up early for this on a Sunday. I was like, what day is it there? Yeah, we're just reversing some ransomware. So, okay, so this is where things kind of start to take shape because it's using a single key across every file. And then I believe there was one more issue with the key as well. I think it might have to do with its length, but I'll have to double check. But because it's a stream cipher, the reuse of the key can enable what's called a key reuse attack, or a known plain text attack. And then basically if you know a plain text file on disk, you can use it to XOR to recover the original key stream, and then you can use that key stream portion to decrypt files. So pretty cool. So let's go back to, so it's mapping the view of the file. Okay, so this is really common ransomware functionality where it's using the restart manager. So what's kind of interesting is, I'm kind of jumping ahead here just because I was looking at the config items, but it'll basically look for processes that have open handles to a file that it's trying to encrypt. And then it'll use this restart manager API to terminate that process prior to encrypting it. and then that will terminate the handle or remove the handle to the file that it's trying to encrypt. Oh, really? Which encryption function it uses? Oh, cool. Okay. I can try and find that. I assume it's this. So this would be encryption function, and then yeah, but it's this, isn't it? Oh no, this looks like the key stream, or the crypto initialization. So if it's 64 bytes, its initial state is 16. Maybe this is salsa, because if it's doing a 64 byte block. Waiting Sun, do you remember? Is it salsa 20? Oh, Abyss, yeah. But do you remember if it's here? I might use let's try Kappa. I just can't remember. So I just put the sample on here. I'll make this bigger. Oh my god, that's way too big. Okay, let's do. I should probably write this to file. Yeah, let's do that. Out. I keep so I have this this synthwave stream open, and then I keep seeing the chat moving on that stream and thinking it's this chat, but it's not. Okay, so I'm just running Kappa to make sure I'm not missing anything obvious. But I am interested. Oh yeah, did our indexer finish? Wait, hold on. I'm gonna check that in a sec. Cryptography. Interesting. Didn't identify salsa or cha-cha. Okay. Oh, do I have to do like the v-vv to make it more verbose? How y'all doing? Is this okay? Does malware mostly use stream ciphers? I think it's kind of either or. There's not really, like, they use RC4 a lot, which is why I went over it in that course, in the courses. But they also use AES substantially. And is it a block cipher? Yeah, XT is a block cipher. So yeah, there's like a bunch of exotic cryptographic algorithms that malware uses as well. But yeah, I would say it's kind of an even split for the most part. Okay, Binge is dying. I'll give it a sec. Hopefully we don't lose our database. But I guess I shouldn't have tried to run the indexer while I was doing stuff. All right, let's continue analyzing this. So I'm just gonna move on from the indexer stuff for now. But if I go back to these, this was responding now. So, all right. So yeah, when I do the -vv flag in Kappa, then we get more details. So if I do salsa 20, okay, so it expand 32 byte values, also part of the both salsa and cha-cha 20 setup. 32-bit words. Cha-cha 20 uses a modified quarter round function. Is it just the nonce size that we can distinguish it with? All right, let's look at the other stuff for now, because I know that's pretty boring. So so yeah, Kappa basically just said it could be salsa or cha-cha. But let's continue looking at this. So this is opening a thread token. Open this one too. And we're getting the token information here with the token groups, and then it's checking if it's equal to a specified security identifier, and iterating over each token, it looks like, or while it's equal to a certain security identifier. Is this free SID? I wonder what this is being used for. Get token information, allocate and initialize SID, pour into the SID. Let's see. I just don't know where this SID is being initialized. Allocate and initialize SID. Okay, fine. Okay, so 220. I don't know if I want to reconstruct this security identifier to figure out what it is, but basically this is just creating an SID and then iterating over each thread token to see if the security identifier is equal to that. So let's just call this ident SID or something. I think it's just making sure it has like certain privileges. Okay, and then this is the pointer to is WoW64 process. So this is dereferencing the argument. Oh, cool, nice. Okay, so or just to show you what I did. So we have the config node that's being acquired using this MW XML config node, and then this function that we found earlier. And then I was like, okay, which config node is it? And it's this global variable. So I double clicked on this, and then we can see that the ASCII representation of these 3 bytes is CMD. So if I just highlight these and hit the A key, then I can change it back to ASCII or a char array effectively. And if I go back here, then this is getting the CMD XML node. And then if I go back to our config that we decrypted, then I can see that CMD is these XML nodes. So it's iterating over each of these XML nodes, which is the shadow copy deletion commands. And then it is executing those in this loop, most likely. So while, let's just say MW get command, this is passing a struct, but we don't have to worry about parsing the struct right now, or reconstructing the struct right now. So this command line cmd/c is copied into this LP command line string, and then they use winexec to execute the string. So let's just call this, or let's just add a comment, say executing config nodes, and then this is just getting the next node here. Okay, that makes sense. How's everybody doing? Y'all all right? All right, and then we have the key generation here. So if we look at the key generation algorithm, this is probably PRNG related. So we have the crypt acquire context, and then the heap allocation that's made to this global, and then the size. I don't see an argument being passed here, so that's probably just the decompiler not showing it. So this push ESI here is the size. If we look at the cross references, oh no, I think that's just the, sorry. It's just accessing relative to EBX, so it's kind of weird. That's just the arg1 offset. So the arg1 is the size, and we saw that earlier, right? Key size. Then we see that's 16. So it's passing 16 to cryptgen random, and the resulting buffer is passed to this thing here. This might be a expansion modulus 94. Okay, so if we go back here to, was it in here? I can't remember. Oh, I thought it was, okay, it's 96 bits or 12 bytes for the nonce. 64 bits or 8 bytes. So 94 isn't what I thought it was going to be, sorry. But this is modding on 94, and then 32 plus 32. So I believe this is going to be expanding the key. But these XMEM registers are kind of weird, so that's why I'm not 100% sure. But then this is being encrypted and then used throughout the ransomware. And this is our, this is where it's setting that default icon. for the encrypted files that I mentioned earlier. Okay, so this is another config node. Okay, so this is getting the icon config item, and then this is base64, I think. Because so if I look at the config again, then we can see that the icon data is in this base64 blob. And then if we look at this parsing code, we could see this is checking for 2 equals. So that's a very good indication that it's probably base64. And then if I look at this global, so I double click on this global here, then if we look up here, this is a part of the base64 alphabet. So basically this is just, those are indications that it's base64. And then if you want to automate it, if we look back at our kappa output, then we can see that it did identify base64. And then if we look at the address that these, or that was identified here in kappa, then this was the MW base64 one that I just showed you. So just kind of 2 ways that you can identify base64 in a given function. Clicking in that struct view. So let's go to that. Okay. So then this creates the icon file, sets it in the registry for the default icon, and it's writing the icon path here. So this would be like a good IOC to look for this ransomware. But this is happening after it's encrypted the system, so it's not great. But let's just do set icon. The only thing I'm not 100% sure about is the extension. I'm assuming the encrypted extension might be generated on the fly here. So what this is doing. Wide chart or multi-byte, yeah. Okay, so I'm pretty sure this is the generated extension. Maybe I'll make it smaller so it's not taking up so much space everywhere. But we can confirm that by, okay, so the heap alloc is happening here. Okay, so it's using get system info. I suspect this is getting some system information and then it's using that to generate and then converting it and then using that as the extension. So we don't have to focus too hard on that because it's not super interesting. But this is, I think this is the main encryption loop. So we should rename this to that. Why is this using wait for single object? Probably just making sure that might be using multi-threading. Yeah, create thread. Cool. So we're kind of working backwards here, back upward. But basically this is the main encryption loop for files identified. It's creating a separate thread for the encryption thread, and then it's encrypting each file and then renaming it with a generated extension after the file is encrypted. If we go back up here, it's getting a specific drive type in this instance to check if these are, so if I check what these enums map to, they might not be in Binary Ninja right now, but if I Google get drive type W, then we can see that 3 maps to drive fixed. So if it's attached to the system, or 4, which is drive remote. So if it's checking if it's a local drive or a remote drive or a network drive. So I'm just adding a comment there. We have this thread that's created. This is looking for fixed drives, so the same thing as before. And then this is looking for, specifically it's looking for Microsoft SQL Server. So this is probably trying to encrypt SQL Server specifically. So MW thread inc SQL Server. And then let's just say this is MW release mutex, and then this is finding files So with this star.star, it's basically just looking for all files within a given directory using find first file. And then it's checking this BlackDB config item. And if we look at that config item in our decrypted config, then we have, it's basically looking for these LDF or MDF. So we can just say this is looking for check. So it's basically trying not to encrypt specific databases, I believe what BlackDB would mean. And then I just keep saving this database as well as we go, just so we don't lose our changes. This is just freeing what we've done thus far. And okay, so let's just call this MW encrypt databases. And it's doing that in a separate thread. And then let's see what these other threads are doing. This might be our like main file encryption function here, because it's looking for white folders. So MW check whitelisted folders. Let's MW check white folders. And then I'll do the other one. It looked like it was checking for the whitelisted files. Yeah, whitelisted files, whitelisted extensions. Okay. And then if we go down here, it's adding a backslash. Okay, I think it's just using that to check if it's a folder. So these are just all little checks to check if it has a dot with an extension. And then if it doesn't, then let's go back here. So let's just call this inc file. But I don't see the actual call. So if these block list checks pass, then I just want to see if it's actually making the call to the encryption or it's writing this somewhere else. I think it might just be performing the check within a thread. So let's just call this check block lists. Check DB block lists. And then it's doing the actual file encryption here, I believe. Yeah. So if it passes the block list, both the types of block lists within a single thread, I don't know why it just doesn't do the, it doesn't just call the encryption within the same thread, but okay, so that's the drive enumeration and encryption functionality. Walk thread. Let's see what that's in the config. Is it a Boolean? Okay, so there's like 15 walking threads, it looks like. So we'll say number threads, question mark. And then this is probably the number of encryption threads too. 30. How y'all doing? You doing okay? Bored? Is this okay? Do you want me to do something else? Is Binja cool? Alright. So we have our services config item. That's then set into this fourth offset of this structure. So I'll just say services struct. And then this will enumerate. This is like also very common ransomware functionality. So it'll enumerate all services using the service control manager. And then if it gets the service that it is targeting, let's see, string and string, copies it. So it looks like it's getting a list here. Is it not actually terminating them in this? Yeah, let's check out. Okay, this is actually doing the termination. So not only will this get the list of services, it enumerates all the services, and then in another thread, it will do all this service termination stuff in this while loop. So it'll enumerate the, let's see. Yeah, it opens the service control manager again. I don't know why, again, it does this in a separate thread, I guess just to try and be performant. But then it'll enumerate all the services. It opens the service and then does a control service call here to terminate it. So if we look at this control code, so control service, I'm just going to Google that API. Then if we look at the control code of 1, then we can see it's service control stop. So it's using that Windows API to stop the service. Let's just say I don't think that enum's in Ninja. Stop service. Okay. So this is a stop service thread. Cool. This is acquiring all the logical drives. So get logical drives is used to acquire every drive letter, which is what it's doing in this case. And then it is iterating through each drive letter here, setting those in a list, and then I think it's sending them to these block list threads, and then finally our multi-threaded encryption threads. And the while loop here, I believe, is likely that config item. And then it's sleeping for 300 milliseconds on each iteration of this, for each encryption thread that's initialized. And then it's basically looking for the total number of encryption threads. So that makes sense. So basically it's looping for the number of encryption threads, and then it'll initialize a thread on each loop iteration. Okay. So let's just call this MW, because that's where it's doing all the encryption stuff. All right, I'm just going to take a quick bathroom break, but I'll be right back. If you have any questions, just throw them in the chat. Love to get questions. So, how's everybody doing? Okay. So we can continue reversing this. We're getting pretty close to being like mostly done this thing. So let's take a look at some of the remaining stuff. So this network share, I think this is a Boolean, right? Yeah, network share is true. And then this is a Boolean, and this is just comparing whether the string is true. And then if the result is 0, then this is going to be opening a WNet enumeration. So if I Google this API, then we can see that there is the WNet open enum function starts an enumeration of network resources or existing connections, and then you can enumerate them using WNet enum resource. So this is just using the Windows API to enumerate network resources, so available network shares on the system. And then it's connecting to each share using a null username and password, and then it will encrypt them within this loop. So we'll just call this network share. And then it'll basically do that for each available network share in the return. So I just named this MW EncNet. So this is all pretty common use of Windows APIs for these types of functionality. Also in this function call here, we have enc local disks, and then this will essentially do the same thing here. So it's just checking if the value within this config item is true, and then if it is, it'll call this MW encryption main function that we looked at earlier. So this will do enc disk and net. Okay, so now we have malware main. This does everything's kind of beginning to take shape now. So we have the config that's decrypted. We have the commands that are embedded within the XML that are executed. Then we have the recycling bin that's emptied. Then the next function does the core encryption functionality for both the disk and the network. And then we have this final function here. So let's take a look at that function. Here we have the Boolean delete event logs. So this will basically check if that Boolean is present again using this comparison while loop. And then it will see that if that is true, then we have this result. And if that is not, or if that is equal to 0, so I assume that means that it is indeed present, or it is indeed true rather, then we have this loop functionality, which will open the specified event logs. So open event log A, and then it'll clear each respective event log using clear event log A. So pretty straightforward. And then there is another config item called shutdown system, which looks like, so shutdown system, if that is present, then let's see here. We have those bat file calls from earlier, and it will, I think, shut down the system by terminating this conhost.exe. What's conhost used for? Is that like a system critical process or something? Hey Goofscoof, how's it going? Thanks for joining. We're just looking at the Donex ransomware that Leon looked at a while ago. Okay, so what was I gonna ask? What does conhost do? Yeah, I saw that talk at Recon. It was really good, which is part of the reason why I'm looking at it. I don't know if we'll look at the crypto flaw this stream, just because we're like 3 hours in already. But I was planning on doing that in the future. I think that'd be really fun. So if I look at this, what is conhost.exe used for? Isn't connected. It's killing the conhost. Killing conhost closes. Oh, really? Conhost isn't connected to CMD and PowerShell. Killing conhost closes cmd.exe and PowerShell. Oh, I see the CLI interfaces. Yeah, nice. Thanks, Daymok. And then, but how is it shutting down the system? Is that in the bash script? It must be in here. This is calling an API. When exec. But that's just the deletion of the bat script. SBBD. Yeah, it must be in the bat script. Unless that functionality is just not implemented. Let's do mw delete event logs. Okay, so we have start, kill, keep. Is that a Boolean as well? Okay, so these are our kill, keep stuff. Okay, so it's just doing task kill for those specific processes. So this batch script will terminate processes using task kill. So I bet this is parsing the semicolons as well. String token, yeah. And then this is probably semicolon, right? Yeah. So that's parsing parse string token. And then that's going to be used throughout. So with the BlackDB items, basically all the config items that are semicolon delimited, it's going to be calling that string tokenizer. How do I get back? There we go. Okay, so it's killing all of those. Is it just doing the bat script for that? Low IO lock. I don't know what this is doing. Exception handling stuff. Just adding a star. Append string. Yeah, I think it's just killing the tasks, and that's it. So let's call mw gen task kill bat. And then I guess this is unrelated to, or I think that might have just been cleaning up the bat files in our other function we just analyzed. Task kill, conhost. Oh, here's shutdown. I'm just blind. So yeah, okay. So it kills cmd.exe and conhost, like Daymok mentioned. Then it deletes the bat script that was used to delete the tasks or the running processes. Then it deletes the bat script. Or sorry, then it deletes I'm not sure what percentage S is in this instance. And then it will shut down the system using the shutdown -r-f-t, I think. If I open my Windows box, I think -r restarts it. Shut down and restart, yeah. /f is force, I believe. Yeah, force closing the applications. I don't really know why you would want to do this. Like restart the machine, but cool. So yeah, I think that's like the majority of the functionality in this ransomware. So let's take one last look. Yeah, I think it's like the majority of it. So what I'll do is I'll put this Binary Ninja database up on GitHub for the premium folks. I'll put the notes up on GitHub for everybody. If you want to check out the next stream, I'll most likely just go over reverse engineering the crypto flaw in this. I didn't want to do that this stream just because it's probably going to take us a while, and then I can have it basically be the majority of the next stream. We can take a look at some of the research Leon did, and then some of the research that the Dutch police did. Yeah, no problem. Thanks for joining. Yeah, if y'all have any questions, here I'm going to shoot the Discord in the chat again. Discord invite. Yeah, sorry, Goofscoof, kind of on the latter half here. But the whole recording will be up as well. Yeah, the premium folks will get the early access to the recording, and then I'll have the recording up later on our YouTube channel. But yeah, there's the Discord link if any of you want to come hang out. And then here's the new Binary Ninja course. So if you want to learn how to do all the stuff I was just doing in Binary Ninja, in a very granular walkthrough fashion, having your learning reinforced using questions and answers and stuff like that, definitely check out the course. I'll just play that ad real quick. So, hey everyone, my name is Joshua Reynolds, and welcome to the Binary Ninja edition of the Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware samples using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective YAR rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply your knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. So yeah, this little ad there. So yeah, thanks so much for joining. I had a lot of fun. I'll get the index stuff working in Binary Ninja as well. But pretty cool to check out the 2.0 features. I'll probably do a 2.0 feature for Sidekick in the future. And yeah, thanks so much for everything. And I'll talk to you all in Discord. Take care.